I'm good. Not really, I'm really bad.
We're going to learn two concepts today, electric current and voltage. The vast majority today is current. Current and voltage are very different terms. If you get them confused, you will fail everything. We are also going to be using current and voltage for like the next 5 weeks. They're a stepping stone, they are a springboard, they're fundamental electronics terms that everything's based on. So let's dive in big time. And for goodness sakes, pay attention. Don't forget to ask questions and engage with this because he's super important. So that's it. I'm going to give you a rough outline, then I'm going to make it more sophisticated 3 times. Here's the overview, and we're going to get more sophisticated in a minute. Half period. Okay, so what is current? Electrical current is the flow rate of electrical charges. I'll explain what I mean by usually electrons at great detail in a minute. Flow rate, what's flow rate tell you? It is a number of things per second. Or is actually asked us to put a number of things. Number of things is actually not how we measure. But the idea is fundamentally, if you were to cut open a wire, look inside, peek inside a wire, magically somehow, I don't know, and count how many electrons pass a given spot in the wire per second, that's current. It's not the same thing as speed. Speed tells you how far something goes in 1 second. Flow rate tells you how many are passing a point per second. Speed tells you the distance, flow rate tells you number per second. Who knows what who's ever seen driven on a road with one of those fancy toll collecting scanners? They're not super common in Arizona. How about just a toll booth in general? At least in a movie or something, right? Okay, so the idea about a toll booth, does a toll booth really care about the miles per hour the cars are going? I mean, if they're going too fast and they hit the toll booth, that's bad. But like, the speed isn't really the important thing for the toll booth. What is? How many cars per hour, right? That's what tells you the toll booth's income for funding the road system. So cars per hour, that's current. Miles per hour, the speed that the cars are going out, that's speed. Of course, there's a relationship. If you've got gridlock, the cars are just barely creeping along, that's not going to be a big current. If you've got a given wire and the velocity of the car charges flowing through it is slow, then the current is small. But velocity is only a part of current. There's more to it than that. I may or may not go into it, tell you the other part. Right now, it's not important. So what is important, I want you to know the idea of current, and I want you to know what it isn't. It's related to, but not the same thing as speed. Don't tell me miles per hour for current. Questions on this one? Okay, so here's a vague picture. Now we're going to get more precise, more sophisticated in 3 different ways. First off, what I told you about charges per second is a lie. You may have heard, don't just stop, listen. Charges, electrons, big secret here, are small. You may have heard that earlier. Yeah, blow your mind here. They're really busy. Practical quantities of electrons, billions of electrons are flowing through the wires in these lights per second. Billions of billions. Order of magnitude 10 to the 18th power. Quintillions electrons. I am not lying. If we were to measure current in terms of charges per second, all of our meters would need scientific notation, or either that or a really long display, right? Yeah, because the numbers are astronomically big. So we invent the idea of the mole, of the dozen, of the coulomb. What is a mole, by the way? Not this one. What's a mole? What's the idea behind it? it's like a dozen. It's not 12, but the idea behind it is the same as the dozen. It's a convenience multiple. Atoms are small, molecules are small. You want to count them out individually in a chemistry experiment, that would be stupid. So we specify the idea of the mole and have conversion factors so that you can measure, take out 5 moles of cyanide or whatever, and do whatever with it. It's far more easier to say than take out so many molecules of cyanide. What's a dozen? It's just the idea that stores don't usually sell eggs by the egg, right? People, bakers, whatever, don't usually care about buying eggs that precisely, buy one at a time and multiple of one. So we invented the idea that carton of eggs carries a dozen eggs because it's a convenient amount to buy at a time. I've got 4 cartons of eggs. How many eggs have I got? I multiplied the number of cartons by the size of the carton. Yeah, that's how multiplication works. Good. I apologize. Please strike this out. I need to fix this slide again. Not 6.02. I do have been writing it down because I was thinking of the mole. It's not the same number as the mole. It's 6.25. 6.24 something. Whatever. 6.25 times 10 to the 18 charge. Okay. So the idea behind how do we measure charges is, well, if you're a particle physicist like I was in a PhD, you can measure individual charges at a time. But for the vast majority of cases, doing electronics, doing anything practical other than particle physics experiments, we don't care about the individual charges. We care about, billions of billions and billions, as Carl Sagan would have said, of charges at a time. So we have this multiplier effect. 1 coulomb worth of electrons is 6.25 times 10 to the 18 of them. So earlier I said that current is measuring charges per second. It's actually measuring coulombs per second. Fundamentally, what is a coulomb? It's just a certain specified number. Like saying that I'm selling, I don't know, 5 cartons of eggs per week, 5 cartons of eggs per week in a small supermarket. You can calculate the number of eggs, just multiply 5 cartons per week by how many eggs per carton, right? That's how we measure amps. It's coulombs worth of electrons per second. Question A in the Google form. If 1 coulomb is the same thing as 6.25 times 10 to the 18 electron charges, what is the electrical charge in coulombs of 1 electron? You may work with your neighbor, put in your answer and hit submit response. Again, the question is find the charge of an electron measured in coulombs. You have dose minutes. Correct, correct, wrong, correct, wrong, correct, correct. Ooh, lots of corrects. We're in the previous section. Oh, wrong, wrong, wrong. Correct, correct, wrong. Okay, hold on, cowboys, hold on, cowgirls, hold on, cow, non-binary individuals. Cowpokes, there we go. Hold on, cowpokes. Good, 60% of you got it. I want to guide you through, not just tell you, here's the answer yet. I will, but I'm going to guide you through thinking through this. I lied again. Pretend I lied again. 1 coulomb is 12 charges. The coulomb number is the same thing as the dozen number. How many eggs, electrons in 1 coulomb? What did I just say? Are there also 12 dozens in 1 egg? No, that's silly. Saying 1 dozen is 12 eggs, that does not imply that 1 egg is 12 dozen. Half y'all told, 30% of y'all told me that there's 6.25, 10 to the 18 charges, coulombs in 1 charge. That's wrong, though. Think about it. If the number were 12, it'd be common sense. 12 dozen is not the same thing as 1 egg. How much of a dozen is 1 egg? 12, right? If 12 eggs is 1 dozen, 1/12 of an egg is 1/12 of a dozen is an egg. What operation did you just do? Think about that and try re-answering the question. This is still question A. Edit response. Think about what I just said. Fix it. Hey, Salma at ASU, JL Calor. Oh, you got it. Okay. M Bonell. Wait, hold on. I need to see a couple more to see if you're not getting any. Never mind. Whole bunch more correct answers. Oh, I'm so happy. Okay, again, the answer. Now I tell you the answer. If 12 eggs equals 1 dozen, then 1 egg equals 1/12 of a dozen. What do? We divided both sides of the equation by 12. If you have 1 coulomb equals blah, blah, blah charges, divide both sides by blah, 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 and you get 1 charge equals 1 over 6.25 10 to the 18 coulombs. Now that number happens to be 1.60 10 to the negative 19 coulombs. That's a useful number too. You should write that down too. What's the charge on an electron? Negative 1.6. Oh, 10 to the negative 19. Don't forget, electrons are negatively charged particles, as you probably learned in chemistry class. Yeah, cool. Look. Take your calculator. 1 divided by 6.25 is all 1.5. It'll be 1 over 6.6. There's something going wrong with it. Okay. Questions. Oh, I didn't tell you. Let me calm down the nervousness for the peeps who not had me before. These are graded based on completion. If you put anything reasonable at all or ask me a question, you get full credit. The in-class quizzes are not graded on correctness. You don't have to get it right. You have to try anything reasonable, anything that's not blank or IDK constantly, with full credit. If you don't know, if you're lost, you can get full credit by saying, give me a question, or tell me I'm confused about this, that, or the other. when I'm scanning through it, I will then see and answer your question. As much as I can.
Okay, so don't panic if you don't know something. Ask me a question or whatever. Okay.
Questions from anybody? Yeah. Negative. So I say one fundamental charge is this many coulombs, one electron is negative that. Yeah, so please take note, please take note. An electron is a negative charge. 1 unit of charge, I guess, although people don't talk about this, people, let's just say is the absolute value of an electron. You could also say one coulomb is 6.25 10 to the 18 proton. But we're obsessed with electrons for a reason. In metals, electrons are the things that are flowing. Electrons are a billion squillion times easier to generate a beam of than protons. Billion squillion, that's the precise value.
Next slide. Question B. B for Bravo. I have a 10 amp hair dryer. That's totally reasonable. How many electrons flow in 4.0 minutes? Should be louder in here. Talk to each other. Two 2.5 electrons is incorrect. No one has ever observed 2.5 or 0.5, any fraction of an electron. Think again. Nope.
No.
No one has ever split an electron. He asked, can you have a half electron? The answer is very no. The answer is not in coulombs either. Hint, hint, hint. What I ask? Not what is the charge that you default to the SI units. How many electrons? Okay, I'm gonna give you one more minute, then we're gonna move on. That's a third of the class, right? Not too shabby. Better than the 3 o'clock section, but not quite. All right. First off, what do you see? I see minutes. Is a minute the SI unit? Did I tell you amperes charges per minute? First thing is, I encourage you as often as you can, you see a non-standard unit, convert it into standard units. 240 seconds. All right, I know the amps and I know the seconds. What can I find? How did I define the amp again? What is the amp? It's how many coulombs per second. So each amp is some number of coulombs per, that means fraction second. What have I got? I give you amps. I give you 240 seconds. What can you find? What's this mean? What's up here? Coulomb. What's Coulomb measure again? Charge, charge, charge. Electric charge. Number of coulombs, number of multiples of that 6.25 number. Okay, so I would say the charge is 2,400 coulombs. What did I ask though? If I've got 2,400 coulombs, how do I get to number of electrons? Each coulomb has how many electrons? 6 point blah, blah, blah. Yeah?
Sorry, for A, what is the in the denominator?
Amps are coulombs per second. So if you got so many amps, you've got how many coulombs per second? I tell you that there are 10 amps, 240 seconds. How many coulombs must have passed? Coulombs worth. Okay, so you got 2,400 coulombs. Are you comfortable with 2,400? Now coulombs to electrons. Coulombs to electron conversion. 2,400 coulombs in this charge times the upstairs 6.25 10 to the 18 I would say charges in 1 coulomb. Final answer 1.5 10 to the 22. Yeah. Good. Come to your neighbor and ask them a question about what's going on. About what's going on in physics class. Tell your neighbor where you're confused. Okay, now you don't have to tell me if you're confused. Of course, you understand everything that's going on perfectly well. Rat out your neighbor. Tell me where they're confused.
Give me a question or two. You don't have to admit to anything. Tell me where your neighbor's confused. Ask me a question. Yeah. And then we made that more sophisticated. We measure not a number of, but coulombs worth. Coulombs of electron is really the upstairs of amps. So as I said at the beginning, the first slide of content is the 1,000-mile view, and then I made it more sophisticated. Another question. Yeah, so watch out for that.
Say the more sophisticated is electrons or charges.
So how do we measure charge? What is an amp? What is the units of how much electricity? That's what charge tells you, how much electrons, how much electricity. But instead of measuring by the unit, the electron, the fundamental particle of it, we measure by multiples of 6.25 10 to the 18th.
But we are going with the number of electrons.
This question asked how many electrons.
Yeah.
So I have to convert at the end of the day from the standard unit, coulombs worth, to what is the coulomb beta. Okay, do another. Question, exercise C. Put this in C. C, oh no, C. Tell me in a number of amps. How many amps? In amps. By default, I've asked current or charge, default amps and coulombs. Those are the SI units. So many correct answers. I'm very pleased. Current is not coulombs. Your unit should be amp. Okay, 30 seconds. Give me your best shot. If you're confuzzled, ask your neighbor. Be talking anyway. Current is not charge. Current is charge divided by time. Current is charge per second. And time's up. Correct answer is 12.
Again, look at the definition. Current is charge, coulombs, per time, seconds. Okay, what happens if I double the charge? What am I doing to the fraction? If I double the upstairs, what have I done? Double the fraction. What happens if I halve the downstairs of the fraction? I doubled the fraction. Right? You have half as much time. You've got twice as much charge per time. If I double something and then double it again, what have I done? Quadrupled. I have 12 amps instead of 3. Again, I would like you to be able to reason about les fractions. Lots of things in this class based on the structure of the formula, not just numbers plugging into calculator. Please think about it this way. If you have a fraction with charge upstairs and time downstairs, if I multiply charge by some number, that multiplies the whole fraction by that number. If I multiply time by some number, that divides the whole fraction by that number. If you have a fraction downstairs, you flippy. 1 over a half is the same thing as 2. Follow-up questions on this sucker. I'm gonna make this short because I think it's utterly confused the 3 o'clock class. In metals, what flows? Most of the time, we're going to be talking about metallic conduction. So what's flowing? Electrons. That's the point of this slide, is to say, yes, electrons flow in metallic conduction, but it is possible for positive ions to flow, for instance, in electrochemistry, for instance, in plasmas, for instance, in the, who's taking MCAD in here? Who knows what an action potential is? You got calcium and potassium ion channels going through your nerve cell membranes. What's a calcium ion, positive or negative? Right? Those are positive currents, carrying positive charges driving these currents. So, the first point here is that this is not a universal law, but most of the time what I'm going to be talking about is electron flow, because I'm more interested in circuits. What happens if I've got 4 amps of positive, 4 positive charges per second going this way and 3 negative charges per second going this way? How many charges per second are going, say, that way? 7. If I've got 4 positive and 3 negative going in opposite directions, you would add them together. Negative charges going this way is positivity increasing that way. Think about it, think about it. I had a house party. And everybody was boring. Well, I was cool, but everyone else was boring. Then they went to my neighbors. Did my neighbor get more or less positive? They got more boring. Their charge went down. As the negative people went that way, which direction did coolness factor go? Well, then it was just me in the house, so I guess it wasn't much of a party anymore. But the positivity coolness factor went in the opposite direction of the charge. Okay, so what's the takeaway? Well, takeaway, electrons are negative. So a rightward current actually for metallic conduction results in electrons moving in the leftward direction. The good news is, whenever I talk about, unless I am specifically talking about velocity of electrons, you don't need to care about this. I will say that the current is 3 amps clockwise. You don't need to care that the actual velocity, the actual motion is electrons going counterclockwise to a certain. You don't need to think about that. There's only one piece of physics this entire semester, and I'll warn you about that when we get to it, that's important. Okay? So unless I'm specifically asking you or I specifically tell you which direction the velocity is of an electron, the opposite the current direction, you won't need to care about it. I will occasionally remind you of this. But when solving problems, you can just say the direction of current flow is this way and treat it as if there were positive things going down. Great. Quiz question delta. D is for delta. What did I just say 2 minutes ago? Charge carriers and metals. What carries current in metals? Just you don't have to write out the word, just say A, B, C, D. This is choice A, this is choice B, this is choice C, and believe it or not, that's choice D. Again, please don't write out the word, just write down A, B, C, D. It's easier for me to quick grade that. E is not a correct answer. The answer is C. C. That's correcto. In metallic conduction, what carries the current? Its electrons. Again, other things are possible, but what we're going to talk about for the vast majority of the time is that. Great. That's what current is. You now know what current is. It's a flow rate measured in coulombs. And you note that the things carrying it are negative. Coulombs per second, I should say. The things carrying it are negative. They go in the opposite direction. It's a bunch of detail. Yes, you do need to know them. But that is a bunch of details. That said, now that you know what current is, let's talk about how it acts. I'm only going to include one thing this slide, this day. We will get more properties of current as time goes on. But this is a biggie. Current is the flow rate of stuff, and stuff doesn't appear or disappear. If 4 people enter a house through the front door, and 4 people enter the house through the back door, how many people have got to leave later? Unless one of them is a serial killer or if they're having sex, 8. Electrons don't reproduce and electrons don't vanish. They're not serial killers. So if you have 4 amps enter a junction and 4 amps enter the junction, what's the current in the third wire leaving the junction? 8 amps. Current is conserved, which is to say, total current entering. What's a junction, by the way? What does junction mean? Place where things come together. Place where 3 or more wires meet. Total current entering a junction equals the total current exiting a junction. That also applies, incidentally, for a single wire. If I look at a single wire, the flow rate, how fast, the rate at which charges are entering any given piece of wire must be those charges are exiting the wire at the same rate. Through an electronic component, a battery's positive terminal spits out charge at the exact same rate that its negative terminal sucks up charge. Electrons are things that charge. Those things do not appear or disappear. So if you've got current entering, it must also exit. Question E. Read carefully. in is towards the meeting point. Out is away from the meeting point. Okay, so think about it. 6 cars are approaching an intersection per minute. Along another road in the T junction, 4 cars per minute are approaching it. How much traffic have we got on the third road? Go to jail, go directly to jail, do not pass go, do not collect $200, 10 cars per minute. Okay, I should say 10 cars exit the junction. Hey, let me ask a follow-up question. Question F. Suppose 6 current, the 6 amps are going leftward in the top left wire. You have six cars per minute exiting the junction, 4 cars per minute entering the junction. What's the current in the third wire? Put that in question F. I've modified the question now. Question F. What is the current in the third wire? The thing that I've circled here. Except if I specifically state you can ignore the fact that the things are negative. You just say there's 10 amps flowing out of a junction. Sure, negative 10 flowing in is the same logically as positive 10 flowing out. That's always true, but that doesn't depend on the electrons being negative. That just it depends on negative left equals right. Negative right equals left. Negative up equals down.
A negative increase, negativity, the negativity charge increase.
No.
Yeah.
Pretend that there are things called positive charges. Charges flowing, amperes, rate of change of charge, coulombs per second. Are those imaginary positive things?
Okay, so that goes the opposite direction.
But that's not to say that amps are negative. Oh, there's grand people up here. Okay, let me tell a story in a different way. I have 4 people enter a house through the front door. Later, 6 people exit the house. There was no sex. What must have happened at the back door? Four people enter, 6 people go out. What must have happened at the back door? 2 people entered. If 6 people exited, there must have been 6 people going in, yeah? Make sense? Question.
Find the one split into 2.
It could totally have 4 junctions. You could totally have 4. Suppose I tell you that there's a current here of 3 amps, current here of 2 amps, current here of 4 amps. What's the current in the last wire? Yeah. Which way? Yeah. Good. Yeah, junction is any place where things meet. An intersection. Yes, but we haven't got there yet. Good questions. Okay, follow-up questions, anybody? The answer to the previous question was 2 in. If 4 people walk into a house and 6 people walk out, 2 must have walked in through another entrance. 2 amperes in per second.
So after 2.
That would be 2 in, yeah. 2 amps in. No, you don't like that. Tell me why.
No, I understand. Getting to it, I guess.
Don't just memorize add currents or subtract currents. Think about which way is stuff going. Got 2 units coming in per second. We've got 3 units going out per second. There must also have been another unit coming in. What goes in must come out. Okay, current is good, current is great, current is one puzzle piece. Here is an introduction to the other. We're going to go into this much more in detail. We're going to go into voltage in much more detail later, but in my experience, preloading your brains a little bit is very important here. Voltage. Voltage is a term that you see all over pop culture, and everyone uses it wrong. Like, nobody understands what voltage really is. I mean, like, except if you take it physics. What is a volt? First off, a volt is a crappily named unit. There are 5 different ways you will see voltage referred to online and textbooks by me. You'll hear it called voltage, electric potential, potential, EMF, electromotive force. Sometimes they will call it scalar potential, but not in the books you're likely to read. I guess that's 6 different names. Like I will always call it by one of 2 names. I will always call it either voltage or electric potential. But your textbook also says EMF, which is why I'm writing this down. In class, I will always call it voltage or electric potential. Same thing. But you also need to know EMF or electromotive force is also just another synonym for voltage. I'm sorry for the proliferation of terms. It's also, there are like 3 different symbols that we use in equations. E&M generally, circuits have crappy notation, I'm sorry. It's all for historical reasons. Okay, so first thing to know about voltage is it's got a million different names. The second, more important thing to know about voltage is energy divided by charge. 1 volt is equivalent to 1 joule per coulomb. You've got 10 volts and 2 coulombs, you must have 20 joules worth of energy. Don't memorize that. Think about what it means. What does it mean? Which is richer, China or Switzerland? China is the 2nd largest economy in the world. Yeah, but the Swiss make bank. Why? China's population numbers, so I don't even remember, it's in the billions. And Switzerland, I think there are like 25 people in the last count.
Yeah, it's like 20 now.
Something, 20 now. Right? It's a small country. So the Swiss economy is a certain number of dollars divided by a small number of people. The per capita is a big number in Switzerland. Right? Which is a bigger energy? China. Which is a bigger voltage? Switzerland. You see? Voltage is per capita income. Energy is total amount of oomph is the GDP of the country. Yeah? It is very similar to chemical concentration. If I've got a 5 molar solution, what does that tell me? 5 molar sulfuric acid. Does that mean I've got a jillion moles of acid? Molarity is not number of molecules. Molarity is the density, the concentration. The number of, what is it? Number of molecules per liter? Is that it? Took chemistry back in 2002. Tell me if that's right. Okay. So voltage is sort of the density, the concentration, the intensity of that energy. It is how is the energy distributed among the charge. Now, as you might have heard the rumor that in China, Switzerland, and every other country on Earth, money is not distributed evenly, at least until the revolution comes. Voltage charges are very egalitarian. They will distribute their energy very uniformly. I've got a battery delivering 9 volts of current. Every 9 volts of voltage, every single electron is going to have an equal share of voltage that leaves that battery. An equal share of energy. So, again, what do I mean when I talk about the voltage across a component? A voltage drop in a component in the circuit is the change in electric energy per coulomb, per number of electrons passing through that component, per electrical charge. Dense concentration. The oomph. Hey, why is it important that, we have warning sign, 5,000 volts in this area? Don't open this box, 5,000 volts. Who cares? Why? Why would you die?
What's important about the voltage being dangerous? If you've got 80 billion electrons with a quazillion bits of energy, that energy can't necessarily escape. Right? If an electron, or if every other electron has enough energy to make a jump from place to place, if the energy per electron is high enough, then the electricity can spark and kill you even if you don't touch the conductor. That's why voltage is important. All other things being equal, who's going to buy more long distance plane tickets per year? The average Chinese person or the average Swiss person, assuming things were actually egalitarian. Now, the Swiss make serious bank. There's more money per person. You're going to see more travel of the higher per capita economy. Yeah? Okay. So voltage is dangerous, high voltage is dangerous because it can jump from place to place. Or for that matter, if you touch a wire, my skin actually is really high resistance. We'll talk about that one later, really high resistance. So very little electrical current flows across the surface of my skin. I can touch a 9-volt battery all I want. Terminals of a 9-volt battery. Utterly safe. I can touch a car battery, 12 volts. Car batteries may have serious energy inside them, but the energy per electron is small enough that I can touch both terminals of a car battery with no risk whatsoever. 120 volts is more dangerous because 120 volts, 120 joules per coulomb can arc through my lipid layers, my fatty skin cells, relatively fatty skin cells, and then what's inside my epidermis and dermis? Warm, squishy, conductive water. My red parts, my guts, are highly conductive. If you have enough voltage to jump through and then back out of skin layers, oh, my heart's going to be having those electrons pass right through. That's what goes on, right? If you touch high voltage lines, the sufficient energy per electron can hop through your skin and actually conduct. Question, follow up.
I was just gonna ask if we're sweating, but
If I am sweating, my resistance goes down, but actually that's still not as important. If I've got energy flowing over the surface of my skin, it's not going to stop my heart. It's really dangerous is current flowing through your heart. Okay. It could burn you on the surface of your skin.
Yeah.
If you lick a 9-volt, it's going to burn, but it's not going to kill you. Question G, real fast. What unit did I say? Is it an amp? Is it an ohm? Is it a joule? You just have to write the letter, 4 letters, or whatever. Yes, yes, yes. 2 inches? What the what? What you talking about, foo? Oh, that's 2 in. 2 amps in. They put it in the wrong column. Yeah, G. G for give it to me, baby. Uh-huh, uh-huh. Give me the answer, that is. Hey, Marcus. Correct answer is volts. I would also accept joules per coulomb. Okay. Okay, don't go. That's it for the slides, but the lab, as I said, first lab of the semester is always interesting. Take a look up here. I'm going to show you some pro tips for what the heck this equipment does. You need to be good at this because, as I said, we're going to be using this equipment for a long, long time. Don't put your notes away either. I encourage you to
to note, to write something down about what this says. Okay, where's the select dot cam left? Now your lab instructor will tell you some of this too. And your lab, I put a PDF explaining this in the Canvas stuff. Oh wait, who doesn't take lab on this campus? You can get out of here. You can get out of here.
We're trying to read that.
Huh?
We're trying to read that.
You need to understand this stuff, and you probably didn't get all the details the first time, so stick around. If you don't take lab on this campus, then you utterly can go. But if you take lab here, let me explain to you briefly, briefly or boxerly, how this sucker works. This is called a proto board or a solderless breadboard. The way it works is underneath these little bitty holes, there are wires connecting some of the holes. The wires lie under these 5 at a time. The 5 at a time will connect anything in this column of 5, not hopping across the channel. This column of 5 all interconnects. So, for instance, if I want to connect 2 resistors, one after the other, I could sit there and hold these 2 pieces of metal together while my classmates do an experiment, or I could simply shove them into the hole. And if you put them in the same row and column, put them in the same column, they will be electrically connected because there's a piece of metal. Please note, an error you could run into is if it doesn't actually slide in a significant couple of millimeters, it isn't making the contact. Sometimes they can like sit on top and you think they're connected, they're actually not. It needs to go in. Are these connected? They're in the same row. The metal is in columns. They have to be in the same column. Okay, notation, terminology. These are called series. Series connection is one connected directly to the next without a junction with no third thing connected. This is no longer in series. There are 3 things connecting. That breaks the seriesness. Oh, now I'm in series again. One thing after another with no third thing connected, okay? There's another thing, another terminology that I describe in the lab manual, but I think it's beneficial for you to see, is if 2 electrical components are connected, not one after the other, but both of their inputs are connected and their outputs are connected. This is called, whoopsie, I got the wrong row. This is called parallel. Their left sides are connected, their right sides are connected. This is in parallel. A third wire coming in and going somewhere else. These 2 are still in parallel. Having another connection to a parallel circuit does not stop it from being parallel. As long as both the left sides are touching and the right sides are touching, that's parallel. If you want to break parallel, you've got to have them no longer touching. This is not parallel. This resistor and this resistor are touching at the left side, but their right sides are not touching. They have this resistor. Okay. These 3 are in series with each other. They're all touching at one point. Okay, so that's the proto board. The second thing is the multimeter. Again, I have a. Hey, hold on a second. No, really, you're like supposed to be. Wait, hold on. It's 40. Do I edit 40 or 45? It's 45, right? Okay, no, so hold your horses, y'all. This is called a multimeter. It is a multimeter because it can measure multiple different kinds of measurements. Yeah, very sophisticated name there. The way a multimeter works, I don't need to know how a multimeter works, but you do need to be able to hook it up. There is a warning if you are measuring amps and you ever have the metal leads, the measuring leads, touch both sides of a battery or things connected to both sides of the battery, the meter blows up. Well, actually there's a fuse inside, the fuse blows, but then I have to get a screwdriver, unscrew it, replace the fuse and put it back together. It's very annoying, don't do that. So, When you are in current mode, never, ever, ever, ever just hook this up to a circuit. You must always make sure when you are in current mode, that you have a resistor along the line of that you have a resistor along the line of the connections. Okay. Never, ever, 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 ever just start poking about in the circuit. There must always be a resistance in series with your current measurements. How do you measure current? Well, one thing is turn the meter knob to the thing that has amps on it. 20 amps, 200 milliamps, 200 microamps. If you want to measure voltage, use the things that have V on it. Volts. Oh, you can't see that. I'm sorry. There we go. Okay. You want to measure voltages? Use the things with V's on them. You want to measure amperes? Measure things with A's on it. Please note these solid dashed out lines and the tildes, the squiggles. That means alternating current. We're not going to do him for a long time. We're going to be measuring DCs. We'll use these settings and these settings. What's the difference between the 20 and the 200 milli? These tell you the maximum that these settings can, these can read. So if you want to measure a current of 3 amps, this is just going to read off scale. 200 milli is way less than 3 amps. So this won't measure anything. This will just have an error message. You'd use the 20 amp setting to measure big current. If you want to measure a super duper small current, this is going to have way more precision. It'll have more sig figs. This will just say 0. If you measure a super small current of 0.001 amp current, 20 will just think it's 0. This says more precision. This says more range. If you measure 5 volts, I would use the 200V setting. The maximum of 5 volts is bigger than 2 can measure, so I go up to the next one. Yes, last thing. There are different ports for different measurements. Black lead always goes in COM. COM stands for communism. No, sorry, stands for common. Black lead always goes in common. And then if you measure voltages, use the lead, the banana connector that has a V on it. Oh, come on, there. It has a V on it. Stick the red in the V if you want to measure voltages. Your meters don't have 2 settings. They just have an amp side. This meter is fancy. This has a high current side. This is for measuring the 20 amp setting. This is for measuring all other currents. Okay, so if I measure a 5 amp current, I would stick the leads like this, red in the 20 amp measuring, black in the COM. If I'm measuring a 3 volt voltage, I put the red in the voltage one and black stays in COM. Your lab instructor will help you with this. Read the manual, the PDF that I uploaded. It's a separate PDF as the how-to. But also, good luck, have fun. And I told your lab instructors not to grade too harshly because it is a lot of new stuff at once. Also, wait, sorry, one last thing. Remember, I love you. Bye.
Sure. So we have 9-volt battery, okay, and we go into parallel. Now, let's say one was a 200. Are you able to calculate?
Yes.
The amount of current going through each one? So you need to-
Yeah, back home.
So ohms law tells you 9 volts is across 100 ohms, carries 90 milliamps, right?
Okay.
9 volts across 200 ohms carries 45 milliamps. How much current is leaving the battery?
Still.
Because the current has the balance. Current entering must be current exiting. Current entering the place where they all come.
So what was the math that you did for the 9 to 100?
V divided by R.
Okay.
V divided by R is R.
Yeah.
Okay. And
What
then,
if they were one after the other? Total resistance is something measured.
and then would there's something about combination.
That you can make increasingly sophisticated combinations. We'll get to that. Okay, that's fine.
So all you do is just do the math of Ohm's law and we'll define each one how much current is going to be.
voltage is possible.
Yeah, thank you. Good to see you. Yeah, I remember last time on the final, saw me coaches. I don't know if you remember, but I was let you know. After my incident, so that's what happened that day. It was actually the night before the final, but it's been a little process. I do have surgery on the 20th. That's Wednesday. So obviously we have. I was gonna let you know if they get that with you. I can email you too.
Fine.
I just want to let you know.
Yeah,
I don't think I'll
the
be.
lowest for participation.
Yeah.
And
And I
I record. Oh, which I need to remember to stop the recording, otherwise it's gonna be. Go on.
And I just know that with that from Wednesday till Friday,